Hello, everyone, and welcome to this presentation on mass timber design and construction. My name is Jordan Terry, and I'm a structural engineer with KPFF. I moved back to Utah about 3 years ago to start the office here in Salt Lake City. As a structural engineer, I've had the privilege to work on some very collaborative, creative teams of architects and contractors and engineers to design and build some cool and inspiring buildings. Although KPFF is relatively new to town, we've been honored to play a part in designing some of the most iconic spaces in Salt Lake City for over 20 years, including the Conference Center and the Trolley Square renovation. As you may be aware, on March 24th, Governor Gary Herbert signed House Bill 54 into law, which expanded the use of mass timber construction in Utah for buildings up to 18 stories. We'll discuss where these tall wood building provisions come from and how they applied in Utah. We're eager to share our experience with this latest trend in construction that has generated a sort of mass timber renaissance. Today, during this presentation, we're not going to go into depth on any one specific topic, but really give an overview of mass timber design and construction. In 2013, this guy right here, Michael Green, an architect from British Columbia, gave a TED Talk called Why We Should Build Wooden Skyscrapers. If you haven't had a chance to watch this one, I highly recommend looking it up. The bar graph below shows data from the Beck Group that demonstrates the number of mass timber buildings that have been built since 2010. You can see that since 2013, there's been exponential growth leading up to 2018. And we believe this trend will continue based on the amount of interest that's out there and as this timber renaissance spreads throughout the rest of the country. Mass timber has been all over in the headlines in recent years, and it's not just in design and construction journals either. As a matter of fact, I gave a similar presentation to the structural engineers in Utah in February, and on my way home, on one of my favorite NPR programs, Science Friday, featured mass timber buildings. That one's worth listening to if you get a chance. Our presentation today will follow this outline. We'll begin with a discussion on why mass timber has become such a hot trend in the AEC industry. We'll then discuss why mass timber, or what mass timber is, and some design considerations. We'll discuss also the recently adopted Utah tall wood provisions. And then we'll end with a few case studies from recent projects that we've completed and they're in different stages of design and construction. The first and most visible reason why people are considering mass timber is the aesthetic. Mass timber has a sort of architectural warmth or biophilia. Biophilia is the idea that humans possess an innate tendency to seek connection with nature and other forms of life. This seeks to explain why we're drawn to these environments. For one recent project that we completed called the Rocky Mountain Institute Innovation Center in Basalt, Colorado, the owner had a vision that this building will create delight when entered, health and productivity when occupied, and regret when departed. To me, this is an inspiring statement, and mass timber was a big part of achieving that goal for that project. Climate scientists have been warning us for decades that too much carbon dioxide in the air will cause global warming. One solution proposed by a company in Canada called Carbon Engineering is a large-scale carbon dioxide removal plant. The image that you see here is a rendering of one of those proposed plants. It turns out that Mother Nature has been creating machines like these for millions of years. They're called trees. Carbon captured in sustainably harvested trees may be stored or sequestered in our buildings, so it cannot be released back into the air as the tree decays or from wildfires. Borrowed from the concept of farm to table, mass timber is providing opportunity for rural economic development and connecting the rural economies to the progress of our cities. This is especially true in the Northwest. Similar to the term farm to table, Lever Architecture, one of our partners on some of these projects, has coined the term forest to frame. In addition, in Utah, responsible forest management also has the opportunity to reduce fire risk in our backcountry. One of the last reasons why mass timber is such a hot trend right now that I'll mention is the speed of erection. Mass timber components are prefabricated and CNC'd to allow them to go together really fast. One example of what's possible is the Brock Commons in British Columbia. This 18-story mass timber student housing project was the tallest mass timber building in the world until recently. Constructed in 2017, the timber floors were erected with a crew of 9. The concrete and core and podium took 7 months to construct, and the timber portion was erected in only 2 months. There's a really cool video that shows the time lapse of the construction. Google Brock Commons time lapse. It's really cool to see this in action. So, what is mass timber? Mass timber is not your parents' or even your grandparents' timber construction. Current mass timber is more aligned with the way your great-grandparents built with wood. Up until the middle of the 20th century, many buildings in our cities were constructed with heavy timber post and beam construction. And one example of this type of construction is the hardware building on North Temple that you see there on the right. Mass timber is not stick frame. It's not a commodity product, and it's not something that you'll go pick up at Home Depot. Unlike heavy timber buildings in the early 20th century, today's mass timber is not created from old growth, large timbers. Today, the new generation of mass timber buildings are made up from building up large sections with smaller laminations. This allows for more sustainable forestry and procurement of timber. Today's mass timber is also highly prefabricated. The image on the left is a CNC machine. Elements are cut, dapped, drilled, routed for connections, and site construction is often more of an assembly of a kit of parts that are delivered to the site. There are a few products that have contributed to the mass timber renaissance. Starting in the upper left is CLT, or cross-laminated timber. To the right of that is NLT, or nail laminated timber. GLT is glue laminated timber. TNG is tongue and groove. You're all familiar with that, I'm sure. DLT is dowel laminated timber. And the bottom right is MPP, or mass plywood panel. Cross-laminated timber, or CLT, was first developed in Germany and Austria in the early 1990s. It's essentially like gluing up glue lam beams, but rather than stacking the laminations in the same direction to create a beam, the laminations are laid up in alternating directions to create large panels. Because CLT is fabricated in alternating layers, the CLT is capable of two-way spans and can also be used as a structural diaphragm or shear wall. On the left here, you see a cross-laminated timber press. All CLT in the United States must conform to this document on the right called PRG 320, developed by ANSI and APA for quality control in fabrication of these panels. NLT is essentially dimensional lumber stacked together and nailed on end. Because all of the lumber spans in the same direction, this is really only capable of a one-way span and cannot be used as a diaphragm. An improvement upon the NLT concept is this product called dowel laminated timber, or DLT. It's essentially the same concept, except for rather than nails, the laminations are connected together with hardwood dowels. When the hardwood dowels come into contact with the surrounding softwood lumber, they swell and lock these timbers together. DLT is primarily fabricated by one manufacturer in North America, StructureCraft, out of British Columbia. The edges of these can be routed or curved for aesthetics, or even to provide an acoustical treatment. And the last product that I'll mention of mass timber suite is mass plywood panel. And they're exactly what they sound like. They're essentially a really thick plywood, up to 12 inches. MPP is fabricated by one mill in Oregon called Frere's Lumber, and they began fabricating mass plywood panel in 2017. Structurlam was the first CLT manufacturer in North America, located in British Columbia. In 2016, D.R. Johnson became the first domestic CLT manufacturer in the United States. In the 4 years since, many CLT manufacturers have opened up, and there's many more in the works. You may also run into European CLT. These CLT manufacturers have distribution centers in North America. One thing to be aware of is that each of these manufacturers fabricate different panel widths and lengths and thicknesses, so it's important to coordinate your design with them. As I mentioned, Structurecraft in British Columbia fabricates dowel laminated timber, and Frere's Lumber in Oregon fabricates mass plywood panel. Wood is different than any other building material. We'll discuss a few of the design considerations and how they are addressed in timber construction and design. First, it's important to understand that wood on a microscopic level is basically like a bundle of straws or tubes that are bound together. This gives timber very different properties in the direction along its grain versus perpendicular to its grain. Some of the practical implications of this fact that timber is strong in the direction parallel to its grain and not so much perpendicular to its grain. When we design and detail these timber buildings, we do so in a way that takes advantage of the strong direction and mitigates its weak direction. Wood shrinks and swells as moisture content changes over time as well. Another practical implication is that the grain structure of wood shrinks and swells across grain of the tree and not so much along the length of the tree. This brings up one of the big differences between CLT and DLT or NLT. DLT and NLT will shrink and swell in its thickness and also in its width. CLT, on the other hand, is dimensionally stable, meaning it will shrink or swell in its thickness, but not in its width or length. This is because CLT panels are laid up in alternating directions, so the shrinkage in width is restrained by the adjacent laminations that are in the parallel direction. Fire is probably the primary reason why we've stopped building tall buildings out of wood. For anyone out there that has built a fire, though, you understand that small kindling burns very differently than do big logs. The IBC recognizes that heavy timber Type 4 building accomplishes fire rating assemblies in very different ways than steel. In steel buildings, we typically protect the steel with spray applied fire resistant materials like monocoat. In heavy timber, however, fire rating is accomplished through a char layer on the wood beam. It turns out that large timbers char at a very predictable rate. We can account for this char layer in the design of these mass timber elements. This is an old image that I like. It's the aftermath of a fire. You can see that although the wood beam is very badly charred, it's still standing and actually supporting the unprotected steel that's draped over it like spaghetti. With mass timber, it's important to understand limitations. The IBC contains prescriptive requirements for area, height, and fire ratings of assemblies. However, sometimes when we're on the cutting edge of building science, we have to step outside the prescriptive code and into performance-based fire modeling and physical testing. I'll show you a few examples of this from previous projects later on in this presentation. Advancements in timber connections and the ability to CNC members to receive these connections is another driver behind allowing us to go bigger and taller with timber. Connections are best if they can take advantage of the strength of the wood. These are just a few examples of connections from recent projects. Connections need to consider the desired aesthetic, the fire rating, the fit-up tolerances, and constructability. Connections can either be engineered or proprietary. The examples that you see here are a few of our engineered connections that we've done. There are some really innovative products out there for timber-to-timber connections. Some of the names down here might seem a little foreign, and that's because they are. Many of the most innovative connections come out of Europe because they're at least 2 decades ahead of us in terms of mass timber construction and connections. Inclined screws, tight fitting pins, self-drilling dowels, epoxy, and concealed connectors shown here are just some examples of the different ways of thinking of connecting timber components. On a side note, the image on the top right is from a fire test with one of these concealed connectors. You can see that the way we oftentimes protect the steel connectors, whether we're talking an engineered connector or a proprietary connector from fire, is with a char layer of wood surrounding the connection. Similar to steel buildings, when you design mass timber buildings for just strength and deflection, that can oftentimes result in bouncy floors. KPFF and Woodworks were recently awarded a USDA innovation grant to study vibration in mass timber buildings. The end result will be a design guide for mitigating floor vibrations in mass timber buildings. To take advantage of biophilic design of timber structures, floors and beams above are oftentimes exposed to view. One of the consequences of this is that the acoustics can be a challenge. This is especially true when you're dealing with multifamily housing. The IBC has a minimum sound transmission class, or STC rating, and also an impact insulation class, or IIC rating, of 50 for multifamily housing. This can be accomplished with a concrete topping above an acoustomat over the CLT floor, as shown in the second column here. Sometimes, however, owners want to improve on this code minimum, especially in high-end or multifamily housing projects. We're working right now on a project in Ketchum where our client wanted to get to an STC rating of 60. This was accomplished with a built-up floor system over the CLT, as you see in the third column. 2 questions that inevitably get asked when contractors are brought on board in a new market is who fabricates and assembles these products, and who will erect the building on site. In more mature markets, this has been resolved in a few different ways. 2 of them. One is the turnkey mass timber sub. This is essentially a subcontractor that supplies, fabricates, and installs the whole timber package. The second way that this has been resolved is some contractors have seen an opportunity to actually self-perform the timber package, similar to the way many do with concrete. Although supply chain and local knowledge can be a challenge right now in this region, this is quickly becoming a non-issue as suppliers and turnkey subcontractors react to market demand. In this region, Red Built has reacted to this demand by developing relationships with SmartLam and Timberworks out of Ogden to supply, fabricate, and install the entire timber package. And we're working with them right now on a few projects. And then along these same lines are the cost of the structure. This is pricing that we've obtained from product suppliers and also turnkey installers on some recent projects. We're seeing ranges of $43 to $48 a square foot for the timber structure. As you might be asking yourself, this is quite a bit more than compared to comparative steel buildings. But a few considerations might make that a bit more competitive for timber. The first one is reduction in finishes, reduced foundations because of weight, speed of erection, and therefore reduced GCs and GRs. As mass timber becomes more widely known and understood in this region, I believe that we'll see these costs come down and be even more cost competitive with concrete and steel buildings. Given that timber ceilings are often fully exposed, and with the amount of prefabrication that goes into these buildings, thoughtful integration of MEP systems are crucial to the success of these projects. Early collaboration between design team, MEP subs, and timber subcontractors is essential. These are not steel buildings, and therefore the typical 30 by 30 bay may be impractical. Here are some efficient base spacings. Standard glulam beam with purlins. We're looking at maybe more like a 20 by 20 bay for an efficient layout. For a CLT deck spanning to glulam girders, the bay size might be closer to 16 by 30. With CLT, we can actually do two-way span slabs. The CLT is directly supported on the columns. The challenge is that you'll end up with a really tight forest of columns. We can get to the 30 by 30 bay with hybrid systems and prefabricated rib panels. And I'll show you a few examples of how we accomplish this later on the Adidas East Village expansion project. And then the last design consideration that I'll mention is there's currently no timber lateral force resisting system in the code. There are two approaches to lateral force resisting systems in mass timber buildings. The most common is a hybrid structure with a concrete core or steel braced frame, or even with a type 3 or 5 building, sometimes we'll do plywood shear walls. The second option is performance-based seismic design. For lateral systems that are not codified, we have to use performance-based seismic design to confirm that the structure will meet or exceed the code performance in a seismic event. Research is underway right now to codify some of these mass timber lateral systems. Platformed CLT shear walls will be codified, for example, in the 2024 IBC. And also of note, Dr. Pantelides at the University of Utah is doing testing and research right now on timber buckling restrained brace frames. So that will be cool. As I mentioned earlier, the state of Utah has adopted tall wood building provisions into their construction code. Historically, mass timber buildings have been designed to a few different construction types. Mass timber buildings generally fall into type 3, type 4, and type 5 construction. With performance-based fire modeling, we've extended this to a type 1B equivalent, and I'll show you an example later on in this presentation. So the 2021 IBC will introduce three new building types, three new construction types. Type 4A, Type 4B, and Type 4C. Type 4 HT is the same as the regular Type 4 in previous versions of the code. Corresponding height, area, and story limits will be found in the code for each of these new construction types, given a specific occupancy. So what the state of Utah has done with House Bill 54 is they've adopted preemptively these code provisions into the Utah Construction Code today. With this early adoption, however, they've amended the allowable heights for types 4A and 4B. I understand this amendment won't be carried over when the 2021 code IBC is adopted. Note that all of the heights and area limits listed here are for sprinkled buildings. Non-sprinkled buildings are allowed in type 4A, B, and C, but they're all limited to 65 feet. And there are other limitations based on occupancy. So realistically, when we're talking about type 4A and B and C, most likely your buildings are going to be sprinkled. Types 4A, 4B, and 4C all have different requirements for fire resistive ratings and prescriptive requirements for the amount of timber that can be exposed. So first off, type 4A is the least restrictive on height and area, but contains the most requirements for fire resistive rating and covering of mass timber. all timber in type 4A must be covered by a protective layer of non-combustible covering. Basically, all mass timber surfaces in a type 4A must be covered in a few layers of drywall. So if your main driver for considering mass timber is the architectural warmth and biophilia, type 4A isn't for you. Some of the research that goes into type 4A comes from Brock Commons out of British Columbia. Although Brock Commons is a really cool case study in mass timber construction, the end product, as you see up there on the top right, looks a lot like any other high-rise housing building. All of the mass timber surfaces are covered in a few layers of drywall. So type 4B is the middle ground. These are allowed to go up to 12 stories, and up to 20% of the ceiling can be exposed. 40% of the wall timber may be exposed. And then there's equation for combining walls and ceilings. And there needs to be a 15-foot separation between exposed ceilings and exposed walls. Again, if your main driver is for considering mass timber as the architectural warmth and biophilia, type 4B may not be for you either. Type 4B is based on some of the research that went into the framework building in Portland, and this is one that we'll discuss later in this presentation. Type 4C is the most restrictive in terms of height and area, but all the timber can be exposed. This is a classic mass timber that many designers have been excited about because of the potential for architectural warmth and to minimize finishes. With this type, you can go up to 9 stories or 85 feet above ground for B and R occupancies. Similar fire ratings are provided for components of the structure for these types of construction as they are for types 1, 2, and 3. One difference, however, with mass timber is the way the fire resistance rating is achieved. In mass timber buildings, fire resistance rating is a combination of the char rating of the timber, the mass timber, and the fire resistive rating of the non-combustible layer that's applied to the surface. However, fire resistive rating doesn't always need to be a combination of mass timber and non-combustible. In some cases, just the non-combustible layer can be used. In other cases, just mass timber can be used. Another thing to consider or be aware of is that the minimum dimensions for heavy timber construction in Chapter 23 of the IBC apply to these new type 4A, 4B, and 4C construction. For types 4A and 4B construction, a portion of the fire resistive rating must come from the non-combustible protection. This table here shows the requirements for the different types of construction. As an example, type 4B, the required fire resistive rating on a floor assembly is 2 hours. Where the non-combustible protection is required, this can be accomplished in one of 2 ways. One is to provide 2 layers of 5/8" gypsum sheathing on the underside of the floor assembly, and then rely 40 minutes for char rating on the mass timber. The second option is to provide 3 layers of gypsum sheeting on the mass timber element to accomplish the entire 2-hour rating. The same is true for beams and other primary frame elements. And then the 2018 IBC and previous versions of the code disallowed concealed spaces in type 4 buildings altogether. The 2021 IBC allows concealed spaces if one of these 3 conditions are met. Option 1 is to provide sprinklers in the concealed space. Option number 2 is to fill the concealed space with non-combustible insulation. And option number 3 is to protect the exposed surface of the mass timber with a layer of drywall sheathing. Now we're going to show you a few examples of some mass timber projects that we have been involved with. I'm not going to go into any great amount of depth with any project specifically, but I'm going to highlight one or two unique or innovative things about each of the projects. This is a map showing some of the mass timber projects that we've done throughout the United States. As you can see, the epicenter of the mass timber renaissance is in the United States, is in the Pacific Northwest. With our headquarters in Seattle and a really strong presence in the Northwest, we've been fortunate to be at the forefront of this emerging trend. So the first project that I'll talk about is the Albina Yard. This building consists of Type 5 construction, and lateral system consists of plywood shear walls. So this was the first project in the United States to use domestically sourced CLT. The press that you see in the top right corner is from D.R. Johnson's facility in Oregon. Another thing that was interesting about this project is this is in the middle of a neighborhood, and the comments from the neighbors was that this went up really fast and it was really quiet, not typical for a construction site. And this is an interior view of the finished product. Wouldn't you love to have your office in this building? So the design and construction of the Albina Yard project provided a proof of concept that was utilized in the design of another mass timber building called Framework. At 12 stories, this framework was to be the tallest mass timber building in the United States. Framework was ahead of its time and well outside the prescriptive building code at the time. So the project team had to be able to justify equivalence using performance-based fire and performance-based seismic design. This project was the winner of the Tall Wood Building Prize competition, which provided $1.5 million in research and development to develop innovative solutions for high-rise mass timber buildings. As I mentioned, the research that went into the design of Framework fed directly into what's now Type 4B construction. There was so much research and physical testing that went into this building, but I'm going to talk specifically about two unique considerations. When building tall wood buildings, one of the first things that comes to mind is fire safety. Since we stepped outside the prescriptive code requirements, we had to be able to justify code conformance. The goal on this project from the outset was to justify Type 1B equivalence in a mass timber building. The team accomplished this through a combination of physical testing of the joints and performance-based fire modeling. This also helped the team understand how much of the wood could be exposed in this building. And then the second design consideration that I'll cover is seismic resilience. The image that you see here is the before and after of the Christchurch, New Zealand earthquake in 2011. One of the big takeaways from this earthquake was that buildings in general performed as expected as it relates to the number of collapse and building damage by the code. However, the image on the right shows the central business district a few years after the earthquake. Although the individual buildings may have met the intent of life safety code, the question is raised, are we as a society satisfied with the seismic design for life safety alone? Or should we push for more resilient communities? So for this project, the team was tasked with two goals for the seismic design of this project. One was to build with mass timber, and the other was to design a seismically resilient system that not only protects life safety, but also can expedite post-disaster recovery. For this building, we had to invent a seismic force resisting system that hadn't been done before. The seismic force resisting system on this project consists of CLT cores, as you see there on the right, and then the gravity frame and the floor panels on the two other images. These shear wall cores aren't fixed at the base. They're allowed to rock up and down. They're called rocking cross-laminated timber walls. or rocking CLT walls. A post-tensioning cable running down the middle keeps the walls from tipping over when the ground moves. When these walls rock up and down, they engage special plates at panel edges. These steel plates are bent into a U shape. All of the damage from the earthquake is concentrating into these U-shaped flexural plates, which dissipate the energy from the building movement. These U-shaped flexural plates can then be removed and replaced after the earthquake, which allows the building the functionality to resume more quickly. In this way, these elements behave much like fuses in an electrical system. Another project that we recently completed in Portland is called the District Office. This project was designed as Type 3A construction with all the timber exposed. This is a hybrid mass timber and concrete core structure. You can see that the surrounding core was left open for mechanical distribution systems. Also, the CLT was laid out in a way that left space between the CLT panels and the top of the beam for conduit and pipe routing above the glue-lams. The University of Idaho basketball arena is a 4,200-seat arena in Moscow, Idaho. The roof and mezzanine level are constructed with glue-lam beams and columns. The roof is constructed with 1 1/8 inch plywood, and the mezzanine level floor consists of dowel laminated timber, all of which meet the requirements for Type 4 HT construction. The main driver for this project using mass timber was the desire of the university to showcase Idaho wood products. The University of Idaho has a thriving forestry program, and they maintain an 8,500-acre forest to the south near McCall, Idaho. The inspiration for the shape of the roof was the rolling hills of the Palouse in Moscow-Pullman area. The gentle slope of the roof presented us with an engineering challenge. Wood is really strong if you can make it into an arch. The shape of this roof, however, didn't allow us to take much advantage of arching action. The 150-foot span of the roof is accomplished with king post trusses. These trusses consist of steel rod bottom cords with glue-lam top cords connected with steel struts in the middle. The portal frame that you see there on the left supports half of the roof with 4 glue-lam beams that are each about 6 foot deep. Here's a recent construction photo of the portal frame. The beam in the foreground is the last keystone beam that will complete the portal frame. The picture gives you an idea of the scale when compared to the size of the outhouses on the left. Another thing to note is the effort that went into the mechanical coordination. The main duct trunk line that provides air to the entire arena was pre-installed in the portal frame with stub-ups between the king post support struts on top of the beam to branch out and feed the whole arena. This project is scheduled to complete in September of 2021, just in time for the basketball season. And then about 80 miles north of the University of Idaho basketball arena is the Catalyst project in Spokane, Washington. KPFF collaborated with Katerra on this project, which is also nearing completion. Katerra is very interested in pushing the AEC industry towards prefabrication and lean design and construction. As such, they've made a big bet on CLT and actually opened up a CLT fabrication plant in Spokane, which provided the cross-laminated timber for this building. One of the innovative things that came out of this project was the lateral system was the first of its kind. Having just opened their CLT fabrication plant, Katerra was very much interested in keeping as much of the building to be CLT as possible. CLT shear walls are very strong and stiff, but they're not very ductile, which is an important characteristic when we design buildings for earthquakes. To enhance the ductility of this CLT shear wall, we introduced buckling restrained braces as the hold downs for the shear walls. Given that this was the first of its kind, we had to go through component testing at Oregon State University and utilize performance-based seismic design to justify the design. The last project that I'll mention as a case study was the Adidas East Village expansion project in Portland. This actually consists of two separate buildings, both of which are constructed of mass timber. The one you see in this image is the north building. The north building is a precast mass timber hybrid. The mass timber double T panels span to the precast concrete girders and columns. With this precast mass timber double T hybrid, we were able to accomplish a wider, larger 30 by 30 bay span and keep the appearance of the timber. I love how the timber and the precast concrete complement one another in this project. You can also see in this picture that the precast girders have been cast with openings to accommodate mechanical distribution systems. As I mentioned, the south building on the Adidas East Village expansion project was also constructed with mass timber. This was constructed atop an existing parking garage, and the lighter material allowed for this addition with fewer upgrades to the parking structure below. Steel buckling restrained braces are provided at the center core as a steel mass timber hybrid structure. I want to thank you for your interest in mass timber and taking the time with us to discuss this innovative new trend. Please feel free to reach out if you have any questions or comments regarding mass timber and potential applications. Thank you.